Okay, I think it's time to get started. Uh, my, my name is Bobby Evans, and I'm going to be talking on Storm, what we've done at Yahoo to scale Storm. So, there we go. So, I'm a architect at Yahoo. I work primarily on Storm, but I also own Spark and Kafka, and in the past I've worked on Hadoop quite a bit, particularly on Yarn and MRV2. So, just a little bit of information about me. The agenda for today is, first I'm going to do a quick overview of Storm and its architecture, talk a little bit about what's already been done, and what's in open source, and what we're currently working on, and what's coming up. So I'm not sure how many of you are familiar with Storm or have used it before. Storm, instead of Hadoop, which is batch processing, Storm processes unbounded streams of tuples. So it's coming live from, say, your web servers, or it's coming from an Internet of Things type object that is sending out information. So the point of it is to be able to process and turn around the information very, very quickly, ideally sub-second. And so there are a few concepts that come with Storm. The first concept is a spout. A spout produces streams. And then you have a bolt. A bolt is a bit of processing logic that will bring in one or more streams, process them in some way, and produce possibly more streams of output. So that could be doing filtering, it could be doing a streaming join, it could be processing some sort of aggregate. And then when you put all of these together, you get a topology. A topology is bolts and spouts that are connected to each other through these named streams. Within Storm, it's a parallel processing system, and so each bolt is a logical processing instance, but there's actually parallelism to it. And you have to have a way to decide. You have to have a way to decide how you're going to route an individual tuple to a specific instance of a bolt. And that's what we call groupings. And so there are several different types of groupings. You can look through them. The details really don't matter that much. It's mostly that it's similar to MapReduce. We can group by a key, or we can do more load balancing or other types of things. So Storm is set up in a kind of nice way. It's for the most part stateless. All state is stored in Zookeeper. All the processes don't tend to keep very much state around, so that way if they fail, they can come back up, pick up where they left off fairly easily. The main process is Nimbus. Nimbus handles scheduling of topologies, decides where they're going to run. It does monitoring. It figures out if something has crashed and will relaunch it. It's what you interact with when you're interacting with Storm. So if I want to launch a new topology, I talk to that. If I want to kill it off or rebalance it, that's what I talk to. Then we have the Zookeeper ensemble. Zookeeper holds all of the state and does all of the coordination. And that becomes very important later on. Then we have the supervisors. So if you're familiar with Hadoop's architecture or Yarn's architecture, the supervisors act very similarly to a node manager. Their point is to be able to run user-defined code, launch separate processes that will run user-defined code, monitor them, make sure that they're still up and running. And they get all of their instructions from Zookeeper. So when Nimbus says supervisor 5 will launch a particular process, it writes it into Zookeeper. The supervisor is monitoring. Zookeeper knows that it's been updated and then adjusts what it's doing to match the state that's stored in Zookeeper. And then finally, we have the workers. A worker is a process that is owned by a particular user and is associated with a particular topology. That's where the actual bolt instances and spout instances are running. And then they will connect to each other and communicate directly. So if I have to send a tuple from one worker to another worker, Zookeeper isn't getting in the way, nobody is getting in the way, it's just the workers communicating directly to each other. Within a worker, we have multiple threads. And so there'll be a thread dedicated to each, well, more or less, a thread dedicated to each spout and bolt instance. And on that thread is where your code will run. But when you're outputting messages or receiving messages, there are a bunch of queues and there's routing involved that Storm handles for you. So you don't have to figure out where bolt 5 is running. You just say, I want to send this off to bolt 5, and off it goes. And Storm will handle figuring all of that out for you. So, what is the current state? What can we currently do with Storm? Well, I'm going to talk a little bit about what we do at Yahoo. So, over the years, we've grown quite a bit in our installation of Storm. And so we've had quite a bit of topology growth, very large topology starting to process massive amounts of data. And so back in 2013, we were very small. So workers already explained, an executor corresponds to that thread. So that bolt or spout instance. And so in the very beginning, when we first started playing around with Storm, we were doing fairly small purpose-built things. By now, we're quite large. We're processing massive amounts of data that are business critical to us. I get called in the middle of the night if things are down. Similarly, with the growth of the number of nodes that we have, so the amount of things that are actually running. Back in the beginning, it was very, very small. And as we've taken off and we've started to get quite a bit of adoption, it's really started to scale. It starts to look a little bit like the beginning of an exponential curve. I don't know how far that's actually going to go or what it is. It's still very early days, but we'll see. So I'm going to go through a little bit of the history of Storm, what's happened with it, and how Yahoo has played with it. So back in 2011, Storm was initially released as open source. And we started evaluating it not too long after that. One of the very first things we did was we wrote a speed of light test to see how quickly we could send messages through the system. We released it as open source. There have been a few people who have taken that and iterated on it, which is great. And at that point, we really were just doing, after we finished our evaluation, we really were just doing some very small purpose-built clusters. So you would have one cluster that was for one particular topology to run. And we still have a few of those people who started doing that, built what they wanted, and don't want to get off of it. But then we started to expand. We wanted to provide Storm as a service, similar to what we do with Hadoop. For Hadoop, we have hosted Hadoop for almost all of Yahoo's infrastructure. So what you see on the front page of Yahoo, what you see on all the news sites, the sports sites, all of these things is really running through Hadoop. And we wanted to be able to provide that same functionality for Storm so that you could get that same information just much, much quicker. And so we started off fairly small. And we started off with a 60-node cluster. And we would have some fairly big topologies, but they weren't huge. So we'd have 40 workers, a few hundred executors. And even at this level, we started running into some scalability issues with Storm. So if we go back to that architecture, it's Zookeeper. So everything is going into Zookeeper. So all the data gets written into Zookeeper. We read out all of that data from Zookeeper. Zookeeper was not designed for massive amounts of data. It was designed for coordination. And we really weren't using it that way. And so at the very beginning, the first thing we did was we set the JUtMax buffer to a large number. This is the number we currently run with. It's about 4 megabytes. No. Is it? I don't remember exactly what it is. I'd have to do the math. I think it's kind of large. By default, Zookeeper only lets you store a few megabytes in, I think it's 1 megabyte inside a Z node. A Z node is kind of like is the value in their key value system. And when I'm compiling a large topology, it got to be bigger than Zookeeper could handle. And so we bumped that up to start out with. We started running into some issues with performance in the messaging layer. Not too many, but we replaced what was 0MQ with a netty messaging layer. Some of that was due to us wanting to move Storm towards Apache and the Apache license. And 0MQ is GPL, is LGPL. And so they don't really play that nicely together. And in preparation for that, we did want to move to something that was much more compatible licensed. But with that also, we did some tuning and we published a nice blog post talking about how you could get better performance than 0MQ using NETI on Storm. In October of 2013, we started running into some issues with timeouts on Zookeeper heartbeats. So each of the workers, each of the supervisors are writing into Zookeeper that I'm still alive, I'm here. And Nimbus would download that data, do some checks to see if it was still alive. And Nimbus was it was taking so long to download all the heartbeats that Nimbus would time out the first heartbeats by the time it got to the end and did the check. And so we had to switch a few things around. And it really just started to show that Zookeeper really was becoming an issue. In late 2013, we decided to take drastic measures, and we turned on a config in Zookeeper called force sync equals no. So Zookeeper by default wants to be very sure it does not lose your data. When you write data into Zookeeper, it's replicating the data at least once before it responds and says, yes, you're good to go. And in addition to that, it's replicated and has hit the platter. It hasn't just been written out to the operating system. The OS has guaranteed that it has synced to the physical media, and we turned that off. That means that if horrible, catastrophic things happen, if all 3 Zookeeper nodes go down at the same time, we may have data loss. But in practice, if all 3 nodes go down at the same time, it probably was a power outage. Everything in the same cluster probably has gone down at the same time, so I'm willing to take that risk. And with that, we were able to increase our performance quite drastically. So instead of doing a few hundred writes per second, we were able to do several thousand writes per second. And now the disk became the true bottleneck that we were, and it was the speed at writing. So we were able to do about 80 megabytes a second. And with these changes, we started to really grow. And we were able to get up to 250 nodes, 400 workers, 3,000 executors. And then we started to actually hit that 80 megabyte limit, which is kind of frustrating. So we were writing out, and the disk was 100% utilized in some cases as we were writing in heartbeat data. And so we started turning on compression. We went through and we figured out that we were reading the data a whole lot more often than we needed to. In some cases, we were saturating the network even. And so we went through and tuned things up and cleaned things up a bit so the load on Zookeeper wasn't quite as bad. At about this time, Storm became a top-level project at Apache. It graduated, which was great. And then in early 2015, so this year, we started working on much more advanced pieces of making Storm scale. It's not just incremental pieces anymore. So we've started looking at grouping and data skew. So when we're doing grouping and you do a key grouping, if you're all familiar with Hadoop, you can get a lot of data skew if you get a bad key, which in Hadoop, it's batch, it's probably not the end of the world. But in Storm, that can be very, very bad because I have one worker that is highly overloaded compared to all the other workers. And I'm trying to process things in real time. And so we now have a partial key grouping where it gives us the power of 2 choices. And so if I'm doing something with a lot of data skew, I can do a 2-level aggregation fairly easily in Storm and avoid that skew. We also added in thrift serialization for all the data that was stored in Zookeeper. That reduced the compression, that reduced the size of the data a little bit, but it also gave us the ability to do rolling upgrades. So starting with Storm 0.10.0, from now on, knock on wood, we should be able to do rolling upgrades. We won't have to bring down our clusters anymore. And with this, we were able to do a 300 node cluster. We have tested higher. We've tested, in theory, up to 800 nodes with some simulations that we did. The theoretical limit is about 1,200 nodes, and I will get more into that later. But with that too, our largest topologies have grown to the point that 4,000 executors, 1,500 workers. So here's kind of a comparison with where we are at with Hadoop. We still have a ways to go. 300 nodes is very, very different from our largest Storm cluster, our largest Hadoop cluster, which is 5,000 plus nodes. And I hear Twitter actually runs a little bit bigger in some cases. But looking at the total node count too, we're quite a ways off from where Hadoop is. And we kind of want to catch up. We have some use cases for operability reasons where we want to have a bigger cluster. I don't want to have to force my ops guys who are in high demand to manage rolling upgrades and all these other things on multiple clusters and multiple data centers. I'd much rather give them one cluster and one data center that can handle both staging and production and know the difference between all of that, and they just have to deal with one set of machines. And we have a few other use cases where people really want very big topologies. Not necessarily one big topology, but the processing they're doing is very large, and so it's multiple topologies all working together to produce the same result. And so our goal is to get to somewhere near, or at least on the level of about 4,000 nodes in a cluster. And so the future work, the current things that we're doing to actually get to this 4,000 nodes. Now, all of these are in some level of development. Some of them we have running right now internal to Yahoo that we're in the process of cleaning up and hopefully pushing back to open source. Other pieces are more experimental, but I'll try and explain those as we go through. So the first reason, why can't Storm scale? And it's about the data. Storm has it's kind of ironic, Storm has a big data problem. It's a big metadata problem. Hadoop seems to have these issues too when we get to these very large numbers. That being able to deal with all the metrics that are happening, and that's what's happening here. And so in Zookeeper, it's writing out to a physical disk. So we could spend lots of money, we could put SSDs in there, we could RAID the SSDs. It's all about how many megabytes a second can I write out to all 3 Zookeeper nodes at the same time. And so we started going back and looking at where is this data actually coming from, what's happening. And so when we write out scheduling data, when Nimbus decides it's going to reschedule a topology, it writes it out. Well, that's the number of the size of this is proportional to the number of executors, because it has to tell where every single executor has to be, times the rate that it reschedules. It doesn't reschedule that often. It reschedules on demand only when things go down. That's hardly anything. The supervisors are heart beating in. And they are heart beating in constantly, but it's a very, very small amount of data. They're just writing in that I'm still alive, I'm running version blah of Storm, and I'm still here. It's the topology heartbeats that really become expensive. And they have metrics inside them, the same metrics that we display on the UI of Storm, to be aggregated. And the really interesting thing, the worst case for it is it's proportional to the connectivity of the topology. So it's not proportional to the size of the topology, it's how interconnected the pieces of the topology are along with the size. So it's the number of, because we're keeping track of the metrics. When I have a bolt, I know how many tuples flowed into that bolt, but I also know where they came from. And so if I have a whole bunch of things writing messages to a single bolt, I have metrics that are proportional to everybody that wrote into it. And so it starts to grow more quadratically than linearly. And what's more, the bigger clusters we have, people suddenly start thinking they can write bigger topologies that are much more interconnected. And so there get to be a very few that really dominate. And so as an example from one of our production clusters, which is a 240 node cluster, ZK was writing out 60 megabytes a second. And 99.2% of that, or thereabouts, was completely from the worker heartbeats. So the worker heartbeats are the thing that we really had to tackle. Now, if you take the limit and we say, okay, if we're going to actually saturate the disk, a spinning disk typically can handle about 80 megabytes a second. If you do a really high-end disk, you can do more. A low-end disk tends to not work quite as well, but it's a good rule of thumb. And so just assuming that we get the same ratio, in theory, we could get to about 1,000, 1,200 node cluster. I don't want to run that high. I'd much rather give myself 50% headroom. 600 nodes is kind of the limit that I would feel comfortable going with. But that's from the Zookeeper perspective. And so one of the things that we're working on right now is what we call Pacemaker. It's a heartbeat server. Twitter, when they were starting to do their scaling, they also wrote out a heartbeat server. We talked to them. They didn't feel like releasing it as open source, so we started writing our own. And the code is written. We haven't deployed it to production yet, and so we're kind of waiting on that before we know that it's really solid, before we decide to release it as open source. The nice thing about it is it's kind of a drop-in replacement for the Zookeeper piece. So the heartbeats, I honestly don't care if I drop a heartbeat. The heartbeats are being written out at a fairly fast rate. Nimbus is reading them in at a different rate. And if I drop one in between, Nimbus isn't going to time me out. If a node dies, if one of these heartbeat server nodes dies, it's sad, but I can fail over to another one, and I don't really lose much of anything so long as Nimbus has a high enough timeout that it recognizes it's still there, it's still alive, it's not the end of the world. And so with that, we decided to just go with something very simple. So it's just a very basic key value store, similar to Zookeeper, but it's just in memory and never writes out to disk. And with that, we now get more linear scalability, so I can add in more heartbeat servers. They don't have to communicate with each other, they don't have to stay in sync, and now the network becomes the bottleneck. But it's not the network of the heartbeat servers, is the network for Nimbus, because now Nimbus has to download all of that data. Sadly, we actually have a few clusters in some data centers that are still running gigabit, and so we decided to go with gigabit as kind of the model. How well can we scale with gigabit, even though 10 gig solves a lot of these problems? And so we looked at some of the numbers for the 240 node cluster. The complete state of a lot of these things compressed was 48 megabytes. Gigabit can do about 125 megabytes a second, rule of thumb. So if we wanted to download all of that in 10 seconds, that gets to about 6,000 nodes. In theory, we could run on a gigabit network with Storm and Pacemaker. And like I said before, it's the connectivity of these topologies that dominate. And so I actually wouldn't trust running 6,000 nodes, even though in theory it could work, simply because, well, for multiple reasons, but also because people will create bigger topologies. And the bigger topologies don't necessarily mean that I can get as much data. They'll be producing much more data. And so 10 gig E should give us a lot more headroom as we move to it. But I still, as an engineer and the person who gets called in the middle of the night when things go badly, I'd much rather have that 2x headroom, the 10x headroom, and try and build it so that it's a system that is stable even on the worst case situation. But then there's more. So we started running into issues where the UI would take a massive amount of time to load. And it was actually kind of comical when we figured it out, that there are two processes. There's the Nimbus process that we talked about, but then there's a separate UI process. The UI process talks to Nimbus using the same Thrift APIs that Nimbus exports to clients. And because of the massive amount of data, we actually had a few topologies that had 400 megabytes worth of metrics data from all the heartbeats, because again, it was compressed. Most of that tends to be text data, and so we got actually an amazing 10x compression ratio. And so there was that 400 megabytes of data that was being sent from Nimbus to the UI process so it could aggregate those numbers and display them on the UI in this very tiny, nice, compact format. And we facepalm moment, what are we doing here? It was the easy thing to do, but we went through, and one of my colleagues spent a few weeks going through and adding in new APIs that would pre-aggregate all of those metrics on Nimbus. Because why download 400 megabytes so that I can send a few hundred kilobytes across the wire? And so with that, we were able to go from some 10-minute page load times down to 7 seconds. And these are for very, very big topologies. Like I said, it's aggregating 400 megabytes of data down into something. The other thing that we've been running into is that there are a lot of people who who package quite a bit of information into their topology. So Storm runs on the JVM, and it packages all of the data that you want for your topology into a single jar, an Uber jar. And some people were producing fairly decently sized jars because they try and put in some other information in there. Say they want to do geolocation and they want an IP to geomapping. Sometimes they try and shove that in there. But also, the more supervisors you have, all of them are trying to download this jar at the same time when Nimbus says, go, start running my topology. And we would get a distributed denial of service attack on Nimbus, which distributed clusters are very good at. If you ever, I got shot once by one of our ops guys in a past life when I was running things on Hadoop instead of building Hadoop itself, where I did a very simple Hadoop fs-ls inside a mapper task. And that mapper task ran on several thousand nodes. And he disabled my account because I was killing off horrible things. So you have to be very careful with what you do because it really scales up. And so with this, we decided we really wanted a distributed cache-like API. So if you're familiar with a distributed cache in Hadoop, it gives you the ability to put in other files, not just one jar, but you can put in all kinds of dependencies and other things and tell it, I want this jar at this location in my current working directory. I want this zip file unzipped and in this current location in my current working directory. But we decided to take it a little bit of a step further in saying, we're Storm. We don't ever want to stop. And so I want the ability to actually automatically update it on the fly without bringing topology. And so taking all of these different things into account, we built a distributed cache, a little different from Hadoop because it has a pluggable backend that's based off of a blob store. So an eventually consistent key value store. And then we wrote a backend that works on HDFS. This also hasn't been released to open source yet. It's in production right now, but we're still cleaning up a lot of the work that we did. We had about 4 or 5 people beat on it over 2 months to 3 months to get it ready so it would go, but the code isn't that clean. So hopefully in the next month or so, we'll be releasing that as open source as well. And that really has solved a lot of the problems for the DDoS on Nimbus. But then we start to run into some very interesting issues with scheduling. And so if you're running on, say, 40 nodes, and you have a very simple network architecture that is a fat tree, and so you have 40 nodes in a rack, all of them have a switch at the top. If all I'm running is a 40-node cluster, life's good. Everybody has point-to-point connections, and I can saturate them, no problem. It doesn't matter where I put things. But as I start to go out and I have more nodes and more racks, then at that point, I'm starting to saturate the top of rack switch regularly, and we've started to run into this, where the probability that the traffic, the tuple I'm sending, is not only off my node, but it's off the rack, starts to go up the more nodes I add, the more racks I add, proportionally to those. And so with that, we've started working on a resource-aware scheduler. There's been a number of people that we've worked with in academia that have done some prototypes, published some great papers on it, and we're in the process of taking those concepts and those ideas and some of their code and putting it into a form that is production ready. And one of the key pieces with this is it's not just CPU aware and memory aware, like what Hadoop does. It's network aware. And it's aware of locality, not locality of my input data, which is what Hadoop does. Well, it is the input data. It is aware that this bolt's input data is coming from another bolt. And what's more, it's aware of how far away those two bolts or these two workers are. And so we will be able to, when this is done, try and co-locate those bolts next to each other, ideally on the same host. If not on the same host, ideally in the same rack. And if not within the same rack, at least enough that we have a fairly high probability that we're not going to saturate the top of rack switch. And then with that too, I can be able to express these spouts are likely going to be able to read so many megabytes per second from Kafka. And these bolts are going to be writing so many megabytes a second to HBase. And with that, I can get a rough idea of how much off-rack traffic is going to be flowing to other systems. And it won't be perfect. We're not planning on doing any enforcement at this point, but just a rough swag of, is this going to saturate the top of rack switch? And if so, let's try and put those things someplace else so that it doesn't become a problem. But with that too, we wanted to have some very intelligent routing of tuples. So right now in Storm, going back to that grouping, there really are two groupings that are very basic. The first grouping is the shuffle grouping, which is I don't care who processes it downstream, just randomly pick one and send it to them. And the Storm implementation will pick one and then do round robin to all the others so that it's load balanced. We have a pull request up for doing load aware routing so that it knows that this downstream bolt is actually a little bit slower. It's not processing things quite as well. And that will give us the ability to start routing around slow nodes. But then Storm also has another concept, which is the shuffler local grouping, where if by chance the bolt you're trying to send to has an instance within the same worker, it's within the same JVM process, it will send it to that worker or those workers within the same JVM process, so I don't take the overhead of leaving that process. Serialization, deserialization. In the ideal world, though, Storm just becomes intelligent. It knows how far away one worker is from another worker, or one bolt from another bolt, whether it's in the same worker process, it's on the same host, it's on the same rack, or it's on a different rack. And then it also knows the load that is currently under. And then, using control theory, be able to guess as to where I really should send this tuple. Start sending it locally until local starts to back up a little bit, then send it maybe to something on the same host. And as things happen, in the ideal world, I start to get no network traffic whatsoever if scheduling has done its job correctly and if the routing has done its job correctly. And so that's kind of the direction we're trying to go in, is to really put intelligence into all of the different routing mechanisms that are there so that you don't have to worry about how big you get, that it starts to scale much more linearly. I have about 6 minutes left for questions. I do want to address Heron. I'm sure many of you already know about Heron, which is Twitter. And then also the Data Torrent guys recently announced that they're releasing their core platform as open source too. I know a lot of these guys. They're all great people. None of it is released as open source at this point. And so I can't really answer how they compare. I haven't done any apples to apples comparisons at this point. When they are released as open source, you better believe that we're going to spin up some clusters and really see where Storm is lacking in comparison to some of these. But I don't really have much more that I can say about them at this point, except that they are interesting, and I am a firm believer in both open source, but also in competition. And if Twitter decides Storm isn't good enough, or if somebody decides that the core piece of Storm just isn't doing what it needs to be, then that's going to give me a kick in the pants. And if I want to keep my customers happy, I'm going to have to hustle and catch up. And so, take those numbers for what they're worth. They're published in the paper. They look interesting, but I honestly think that we are at most a few months behind, in the worst case, in being able to match most of those numbers. So if you do want questions, they've asked that you speak into the microphone just so they can record them.
So we have a pretty small cluster, but I was curious, since you guys have so many nodes, can you talk a little bit about how you monitor the errors that you get from the topologies, and more around monitoring and alerting and debugging?
Yeah, so we've had a lot of questions about debugging. One of the features that we've been working on that also isn't in open source but should be coming soon is better logs. So recently, as part of the 0.10.0 release, which is still being voted on, should be out any day now, we switched. So originally Storm was using log4j, then it switched to logback, and now we're switching back to log4j, but it's log4j2 this time. The API should stay compatible, but with this, we're getting better ability to export the logs through syslogd. And so one of the things we've been doing is we've been taking those logs, exporting them to syslogd on the local host, having the local host then export them to, not Splunk, we use Logstash with Kibana right now for it, just to give users a better view into what's happening. We make sure that syslogd is set up so that it throttles, so that it's not saturating the network, it's not interfering with other things that are running. And so in a few cases, we made drop logs. Debugging distributed systems is not a solved problem. And so typically we have people, they will do some debugging on local mode, where they'll run their topology in a smaller set, and ideally they can reproduce it there and then step through the code. If they can't, they'll call us up, and sometimes we'll log onto the box, bring up the profiler or do very basic things with that. A lot of it does come down to printf logging and debugging that way, which is really horrible. I really wish there were something better, but we just haven't had the time. Hadoop has the same problem. And it's really scary when you see that some people will output more data in their logs in a Hadoop job than they actually will output in the final output. Yeah?
With the improvement side, today we are in the Netty layer. We are using the version of 3.x, I believe. So if we move on to the latest version of Netty, we might have to rewrite the APIs on the Netty side, which Storm is using. But there is some improvements on the Netty also with the latest versions. So is there any plans to move to the latest version of Netty?
I don't have any plans at this point. A lot of it, so if you went to the Twitter performance talk yesterday, I'm a firm believer in also measuring before you make any changes. And that's a lot of the reason why we had the speed of light test. And so I haven't measured that at this point. And so I don't really know for sure if Netty really is the bottleneck in a lot of these cases. That a lot of what we've been looking at is scalability, not necessarily end-to-end performance. And it's not a scalability issue at this point to be able to have the older version of Netty. We do plan to start looking at the performance and doing performance optimizations very soon. But a lot of our concentration has been right now just getting it to scale up to the level that we are running at and making sure that it is very stable.
On your largest Storm clusters, how many nodes of Zookeeper do you run?
It's between 3 and 5. And So Zookeeper scales interestingly. The more nodes you add, writes get slower, but reads potentially get faster. And it's mostly been writes that are the problem. We were reading a bunch of things, but what we do with Zookeeper is we actually, before we read the data, at least anything that might be big, we'll check the version number because Zookeeper has a version in there. And we can say, do I actually have to read it? Has it really changed? And if it hasn't changed, I don't read it. And that dropped down the read load drastically.
Is what is the number of storm topologies I can run in a cluster? Is there some kind of a estimate of how many topologies can I run in a?
It varies. So a lot of ours will have a few hundred. We've done some tests where people were trying to translate a. We've had some people trying to write a language that would translate into a storm topology at a kind of a high level. And I'm not sure where it is. We haven't dug into it yet. But as you start to get to more than 500, 600 topologies, interacting with Nimbus really starts to slow down. I think it's an issue with locking around Zookeeper, where we're grabbing a lock before we interact with Zookeeper. I don't know the details of what's happening there, but yes, it was getting up into a few minute range to launch a topology when we were, in my tests when I was running more than 2,000 topologies. So there are some limits there. It's in the couple hundred topology range right now, but it hasn't been enough of an issue for us to go fix it.
And we're out of time.
Yeah,
We're out of time.
yeah, we're out of
need to
time.
get
We
on
can
to the next
talk more
presenter.